In this section, we are going to learn about fine tuning. So, what is fine tuning, and especially the basic idea of the fine tuning? We can use the full fine tuning. We call it full. Okay. What does it mean by full? Full means we use everything. We use all the weights. We already learned. We can use the features and the parameters, learn from some tasks are useful for another task. So if you look at this diagram, suppose we have the source data like BERT. So BERT is the pre-trained model. We use the pre-trained model and we create the model together with the source labels. We can create a new model after we create a new model from our data and then from BERT, and then we can transfer into a new model, which is the target model. And this new target model, we will leverage with a new data. For example, I have a new data from movie. So BERT, actually, it is only a collection of text. But the target data movie, it is the review data from movie lens dataset. So there are many reviews about movie, and we want to analyze this data. Let's say we are going to check the rating, or we are going to check the sentiment. Then we can use this data to build the target model, and we can check what is the sentiment, or what is the category, or what is the class. And we call this is the small amount of data or small amount of labels, because maybe we have only 10,000 data, or we have only 5,000 data. This is so small. Meanwhile, BERT and the other kind of data with source labels, we have maybe 10 billion data. So we can leverage those big data into the small data. Okay, the first we want to look at the full fine tuning. The idea is just selecting the pre-trained model. Okay. When you have a pre-trained model, it means you have the weight and also you have the bias. So I hope that you already learned from the neural network. Okay. And after you prepare this pre-trained model, you need to prepare what will be your target or the task specific dataset. And you need to fine tuning the model. We call it, this is fast forward. And you can do the backward pass or back propagation. When you do this back propagation, it means you are going to update the weight. So weight updates according to the loss function. Yeah, I will not explain in details about the neural network, but this back propagation, you can use any materials from the neural network to understand how we back propagate. Now you can see a lot of LLM. There are many kind of LLM nowadays. We can use the open AI. We can use the DeepSeek, BERT, and etc. We call this is the large corpus of data. And we pass forward along with the task specific data set. So if you cannot get a lot of data, maybe you have only, Professor, I have only 500 data. Is it enough? Yeah, you can try. Okay, with this 500 data, then you can fine tune into the existing LLM. After you fine tune it, then you can use this model to predict something. So you can do the text classification, you can do the sentiment analysis, you can do the text summarization, and so on. So we have the pre-trained model. You need to select what is the pre-trained model. You need to have the task-specific dataset and then fine-tune it. After you fine-tune it, later on, you need to get a new weight, and this new weight, we can update the weight based on the back propagation. Then it will be a loop until you get the best weight, and the best weight will be used for the final model. For example, okay, let me just make it a very simple number. Okay. I have the word I like cats. Okay, so there are 3 string. Okay. So this 3 token, okay, I like cats. If you still remember, we need to build a kind of encoding. Okay. We have the embedding. In the embedding, you can get a number to represent this word, and this word. Now, let's suppose we have the sentence embedding for this one, for this sentence. The array is like this one, 1, 2, and 3. So this is just an example for easy explanation. Okay. Now, after we know that this is the embedding, we will use the pre-trained model. Okay. So what is the pre-trained model? Let's suppose this is the model. When you have the neural network, you will have weight. So this is the weight, and this is the bias. Okay. We always have the weight and bias. The weight is 2 multiplied by 3 matrix, and then bias. So for example, this is 2 1 row and 2 columns. Now we already have this model, and you need to specify what is the task. We have the task specific dataset. So let's say this is your dataset, and we are going to do the fine tuning. Now we need to get the adjusted label for the binary classification. Just example, we have the target is y equals to 0, 1. So what does it mean? For this word, we have like binary classification, 0 and 1. Okay. So let's say 0 is, I don't know, negative. Okay. Just example. And maybe 1 is the positive. Okay. So this example target means that we are doing the classification 0. Okay, this is more on the negative, and this is more on the positive. So let's say this is, we have the adjusted label. This is the positive. After we already know that this is the step 1, now we need to do the fine tune. Okay. How to fine tune? If you learn from the neural network, we have the softmax function. Okay. So the softmax function, it is, we need to get the z value, and the z, usually it is a kind of multiplication, matrix multiplication. In the matrix multiplication, we just do the multiplication from x. X, it means the embedding. This is the data that we have, which is 1, 2, 3. This is from the embedding from I like cats. And then we multiply with the weight. So the weight is the pre-trained model that we have, and we usually use the transpose function. So it depends on how we can determine the weight, but most probably we will do the transpose from the weight, and then we will do addition with the bias. Then if you have this array or this matrix, multiply with this matrix plus the bias. Okay. Then you can get this one multiply by 0.1, and then 2 multiply by 0.2, 3 multiply by 0.3. This is the first, and then we also need to multiply 1 with 0.4, 2 multiply with 0.5, and 3 multiply with 0.6. Then we got this value. After we do this multiplication, we will add those value with the bias. So this is the bias. And you will get the Z value is 1.4, 3.2. Okay, so this is from this one. 1.4 is from this one, and 3.2 is from this one. Because we already have the Z, you can apply the softmax activation. So what is softmax? In the formula, the softmax is using this formula. We have E power of xi divided by the summation of E where we have the Z. So the Z is this one. So what is xi? Xi is the element of this Z. So this is the xi. It means we want to know the prediction on the first class, and this is the second probability of prediction in the second class. Then we will get the softmax value when the Z is 1.4 and 3.2. It means we will do the exponent from the E, the natural number E. So E power of 1.4, which is the value from the first, divided by the summation of Ez. It means this is from the Z value. E power 1.4 plus E power 3.2. And the second number will be E power 3.2, which one from this, divided by E power 1.4 plus E power 3.2. After we do this calculation, we got this number. Okay. So please check later how to operate with the natural number E in your calculator. Okay. I don't know if you can have this kind of problem or not. After you get the softmax, this number, then we can calculate the loss function. The loss function is the loss function from the binary classification. This is the cross entropy log, the loss using the log function. We have minus sigma of yi, and we do the log of the y hat I. Y hat is the predicted value, and then yi is the ground truth or the target that we want to check. In this case, we know from the previous target, the example target is 0 and 1. And then we want to check, the target is 0 and 1. And the predicted is 0.14, 0.86. How we can get this one? It was from the softmax function. Then the loss will be, you can just embed the value, which is the 0, means this is the probability for the first class log 0.14, plus this is the probability of the second class, which is 1, multiplied by the log of 0.86. Then we can get the loss is this one, 0.15. After we get this loss, now the question is this small or big loss? We want to minimize the loss. This one should be minimum. In order to get the minimum loss, then we need to update the weight. We need to update also the bias. Then you can do a kind of gradient updates and weight update. You can adjust the weight. In order to adjust the weight, you can use the gradient descent. The gradient means we want to get the delta W. The delta W means we want to get what is the difference between the weight and the weight along with the loss. So this is from the back propagation. After we adjust the weight, then we can update the weight and use the gradient formula for the weight updates. We will check again the loss after we get a new update. It is a kind of repetition. So it will be repeated until we got the minimum, or sometimes we have a kind of parameter, the stopping parameter. For example, I want to run 100 repetition, or maybe sometimes you have the epoch. It is to stop the training and etc. After we stop, then we will show the final loss. The smallest loss it will be used, and we will perform the fine tuning with the latest weight. That's the loss of the fine tuning. The other kind of way to do the fine tuning is knowledge distillation. Knowledge distillation. The word knowledge distillation, it means we want to learn a source model and distill its knowledge to a target model. Okay. Distill means we want to extract. Okay. We want to find what is the most important knowledge from the source, and we want to use it for a target model. It can lead to a better model with small architecture or faster training. Okay. So they mentioned the knowledge distillation, it is a kind of teacher and student. So the source or the teacher model, it will be a huge layer or a huge model. So given a teacher network on the domain D, we want to enhance the training, usually a smaller a student network on same domain D, using the knowledge of the teacher network. So it means with the student data, I have already the teacher model, and this is higher or bigger model. You can say we have, for example, we have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 layers. But the student model, we have 1, 2, 3, 4, 5. There are 5 layers. So using the 5 layers from the target model, we want to match how to match between the teacher and the student, and we will use this matching for the prediction. It is done by matching the output source and the target model. So we have the weight here and we have the weight here, and then we are matching the output. And once the output already matched, then we will use it for the future task. We can design a new loss term if it is a kind of probability, then we will use the MSE loss, the mean square error loss, or in our case, we can use the KL divergence or the Kullback leverage. So we can see later. So this loss term is to make a new source and target matching output. It is in order to check the similarity. Okay. How we can check the model is on the original loss term. So in the knowledge distillation, we have a new parameter, we call it temperature. So the temperature, it is to make a softer probability distribution over classes. So if you learn about the softmax, okay, from the previous example, the softmax means we have the exponent of xi or the exponent of the zi divided by the sigma of exponent of z. So it means we want to do the summation for all values in the z. But now we do not want to use only the z value. We do not want to use only the z value. We want to use the temperature T. So T is the temperature and it is to softer. What does it mean by softer? Sometimes we need to soften the Z value. If the T, yeah, we can adjust the T becomes high or small. Okay. So if it is high, then any value Zi divided by a high value, for example, divided by 10, then the value will be very soft or it will be very small. Or sometimes we can also use the temperature less than 1. Let's say we have the Zi divided by 0.1. If the temperature T is 0.1, then this value will be bigger. Okay. So it depends on your data. Usually, we want to get this temperature in between 1 until 5, or it depends on the data. Maybe it can be also 0 until 1. Okay. So this temperature is very random values. And we have this kind of formula, Zi. Zi is the one that we learned from the previous example. We can get the result from the softmax. And then Qi, we call this is the logit. No, sorry. Zi is the logit and Qi is the probability. So we have the Qi, in this case, Qi given T. T is the temperature. So the soft target, after we already got this result, the Q with this formula, then we can check the loss function. So the loss function will be 1 minus alpha. Alpha is a kind of weight multiplied by the loss CE. The loss CE is the cross entropy. At the loss of cross entropy, we can use the minus sigma yi multiplied by log of yi predicted, like what we learned from the previous example. We want to compare the y, which is the actual value from the class, and q. Q is the result from this one, plus the alpha, which is the weight, multiplied by a temperature, power of 2. Okay, so this is the temperature. And again, we want to get the cross entropy from the P and Q. This P is the source model output and Q is the target model output. Okay. So it is important to multiply soft targets by T power of 2 because the magnitude of the gradient produced by them scales as 1 divided by T power of 2. The basic loss function, if we use this is the cross entropy. The other kind of loss function, we can use the Kullback-Leibler divergence with this kind of formula. So P means the source model output and the Q is the target model output. So we want to minimize this one in order to check the loss. So let's see how the knowledge distillation with the example. So first, we need to compute the teacher prediction with the temperature T. And after we do the computer teacher prediction, we check the student loss. After we know the student loss, so we can check the total loss. After we have the total loss, then we will back propagate and do the updating on the weight. Now, let's suppose I have only x1 and 2. So let me just make it simple. There is a value 1 and 2. Maybe this is a kind of word, hello world. There are only 2 words, and this is the embedding. The embedding for the word hello is 1. The embedding for the word world is 2. When we do the teacher model, we want to do something with the neural network. Now, let's say with the temperature T equals to 2, we got this output. Okay, so this is the teacher model output. This is the teacher model output. And then after we do with the neural network on the student model, with the smaller model, let's say we got this output. We have the ground truth label. So 1, 0, 0. Maybe if we use the classification, this is maybe positive. This might be neutral. This might be negative. Okay. So let's suppose there are 3 labels. Now, after we do have this teacher model output, we do have the student model output, we have the ground truth label, and we have the input. We can calculate the loss function. Okay, we can calculate the loss. First, we need to calculate the teacher prediction. The teacher prediction with the temperature T means we do the softmax probabilities from the teacher model with the temperature T. We use this formula. As I mentioned before, the P teacher, or after we do the softmax, the original softmax is just the exponent of xi or the zi divided by the sigma of the natural logarithm with the zi. But because we want to consider the T, the temperature, then the formula will be, this will be divided by T, and we have the sigma zi divided by T. Given the P teacher 0.7, 0.2, and 0.1, assume they are already softened by T equals to 2. Oh, I think this one, T equals to 2, like this one. Next, we want to get the student loss. We want to get the student loss. This is the distillation plus the ground truth. So for example, I have the loss from the teacher. I also have the loss from the student. I can say that the total loss is the combination of distillation loss. As I mentioned before, the student will mimic the teacher, or the students want to know the knowledge from the teacher, and we also need to check the ground truth loss, or how the student align with the true labels. And we can define the weight. The weight means whether we want to put the loss more on the distillation loss. Distillation loss, it means the loss between the teacher and the student. And the other loss is based on the ground truth. So whether the ground truth loss or the students loss with the true labels is good or not. So usually we want to balance it, or we can use the alpha 0.5. It means we want to get the distillation loss and the ground truth loss equal. Okay. Or if we want to say that the distillation loss should be higher, then we can make the alpha is 0.6. It means if 0.6, then the distillation loss will have the value 0.6 and the ground truth loss will have 0.4 because it is 1 minus alpha. Now let's just do this with the KL divergence between the teacher and the student. So the loss distillation we can apply with the KL divergence. It means the T power of 2, the temperature, multiply by the sigma, the output from the teacher model, multiply by the log of the teacher model divided by the student model. Okay, so you can get like this one. It means when we do the log distillation with this formula, We know the P teacher, we know the P student, and we know the T. The P teacher means this is the model output from the teacher. The P student, this is the model output from the student, and this is the temperature. You can just put into this formula. 2 power of 2. So this is from the T. And then we do the sigma. Sigma means this is the data from the teacher, 0.7 log 0.7 divided by 0.6, 0.7 divided by 0.6 plus 0.2 multiply by log 0.2 divided by 0.3, 0.3 plus 0.1, which is this one, multiply by the log 0.1 divided by 0.1. Then you can just calculate this one. At the end, we got the value. The loss is 0.1072. And after you got this one, we can calculate the ground truth loss. So the previous one, it was the distillation loss. Now we can calculate the ground truth loss. The ground truth loss, we use the cross entropy loss. So this is the cross entropy loss. We have the minus sigma yi log the P student or the output from the student model. This is the ground truth. Before we have 1, 0, 0, and the student model is 0.6, 0.3, 0.1. Then you can calculate the loss function immediately. We have 1, which is the yi, multiply by the log 0.6 plus 0 multiply by log 0.3 plus 0 multiply by the log 0.1. Then overall we have minus log 0.6, and we can get the loss function is 0.511. After we have these two loss, the loss of distillation, we have the loss from the distillation, and we got the loss from the ground truth. Then we can calculate the total loss based on the alpha. So we already say that the alpha is 0.5. If the alpha is 0.5, then we put the 0.5 multiply by the loss distillation. This is the loss distillation. And then 1 minus alpha. 1 minus alpha means 1 minus 0.5. So this result is 0.5 multiplied by 0.511, which is from the loss with the ground truth. Then we get the total loss is 0.3091. So this is the total loss from this knowledge distillation. Although we know that that is the loss, so we can do the back propagation. So the back propagation or the weight update means we will check the gradient. The gradient for the student models are derived from the total loss. And we are using the combination of the gradient from the distillation loss. Distillation loss, this is from the teacher and student after we soften the output. And we also use the gradient from the ground truth loss, which is aligned with the true labels. Again, yeah, this is the loss from the distill. and this is the loss from the ground truth. So using this combination, we will update again the weight, and again we will get the P teacher, and we will get again the P student. After we get the new P teacher, after we get the new P student, again we will calculate the loss, and we want to get the minimum loss. When the loss is minimum, okay, here, when the loss is minimum or nearby zero, then we will select that model for our prediction. Okay, so let's have a break. Okay, I will continue after the break.